no, it's just pi. So I'm going to just draw in my x-axis. And remember, over here is pi, and we start at 0. I'm not even going to draw in the y-axis right now. So angles in standard position start on the positive x-axis. This is a negative 9 pi. So Evan, what way would this angle rotate if it's negative?
I'm sorry, what'd you say?
What angle would a negative angle, which direction would a negative angle rotate?
Clockwise.
Yeah, so we're going to count negative 9 pi. So if I go clockwise underneath, there's 1 pi, and then all the way around is 2 pi. So I just need to keep going. 3 pi, 4 pi, 5 pi, 6 pi, 7 pi, 8 pi. And then I need to get to negative 9. So the negative tells you the direction, and then the 9 is really the number of times you're kind of rotating around. So notice that that location is on the negative x-axis. So if I finish my angle, the angle is actually a 180-degree angle. The location, though, is on the negative side of the x-axis at the value of pi. And that ordered pair, so I have my angle. The second part was to write the ordered pair is negative 1, 0. And then you were asked to find all of the trig functions. So the sine we said was the y, and the cosine is the x. And that's because the sine is the opposite. Well, there really isn't a triangle drawn, so that height would be 0. And the cosine is the adjacent. Well, the adjacent of this triangle that really isn't there is the x value of negative 1. And then the tangent is y over x, which would be 0. The cosecant is 1 over 0, which is undefined. You can just write a u. You could say undefined as well. The secant is 1 over negative 1, which is just negative 1. And then the cotangent, again, is 1 over 0, which is undefined. Does anybody have questions with letter F? So that like similar type of angle was given. 5 pi was on the worksheet due, or the homework due yesterday from the book. And then this angle, the sketching of it is very similar since it's just dealing with pi. All right, so we're going to look at some right triangle trig today. In your packet, it's section 4.3. Today, I think, is the straightforward right triangle trig. Tomorrow is a little more interesting because we're going to pull in some trig identities and try and use those. But today, we're just going to talk about some right triangles. So section 4.3, that's what I wanted to do. And this is page 25 in the packet that we're working on. So in section 4.2, we talked about the unit circle as one of the two perspectives of trig. And Jack, I think it was you who said what a perspective was, if I remember correctly from a couple weeks ago. Do you remember what a perspective is, Jack?
I do not.
Oh, okay, so then it wasn't you. I'm just thinking that it was. So a perspective is a way to view things. There are two perspectives of trigonometry. So two different ways to think about it or view it. One way is the unit circle, and the other way is right triangles. And that's pretty much the way most of trig is created, either from the ordered pairs on the unit circle, so all of those ordered pair values as you spin around the unit circle, or by creating a right triangle. And that's kind of the ways that I can think about trig and finding a lot of information about trig. Trig is the study of triangles. So this first part here, we already talked about if you have an acute angle from 0 to 90 degrees of a right triangle. So it has to be a right triangle. All of the triangles that we talk about in this chapter are right triangles. So everything is based off of or dependent upon a right triangle. You can place that angle in either location, but we know with respect to the angle, now this is back to like just regular right triangle. If I go across the angle, we call that our opposite side. Next to the angle is the adjacent, and then the hypotenuse is always the side across from 90. We already discussed this really. I did this as my pre-trig unit or a little day of review. But instead of saying it's X and Y, that deals with the unit circle. This is just dealing with a right triangle. So if I wanted to find the sine of the angle, we know that the sine is the opposite over the hypotenuse. As I said, we've been talking about this, so this is really just review. The cosine is the adjacent over the hypotenuse. And the tangent, we know, is the opposite over adjacent. And you can see underneath, I have in bold SOHCAHTOA just to remind you. I don't think you need it, but just in case. So the only difference from the pre-trig worksheet to section 4.3 is that now we know there are 6 trig functions, where you only realize that there were 3 until 3 weeks ago. So the other 3 functions are those reciprocal functions. And we have the cosecant. So Darby, if the sine is opposite over hypotenuse, what would the cosecant be?
Would it just be opposite hypotenuse over opposite?
So if they're reciprocal functions, how could I take the reciprocal of what the sine function is? What would that mean?
Flipping it?
Yeah, flip it. So then it would be?
Hypotenuse over opposite?
Yeah. Is that what you said?
Yeah, but that's okay.
Okay. In my mind, I just didn't hear that. I apologize. So then if you want to find the secant, you just take the reciprocal. And it would be the hypotenuse over the adjacent. Again, in terms of the unit circle, it would be x and then 1 over x. But this is just a triangle. And then the cotangent is the adjacent and then over the opposite. So we're going to see if we can do some right triangle trig for all 6 trig functions instead of for the 3 trig functions. Now we know there are 6 of them. Sometimes you'll be given a triangle. Sometimes you might just be given a value for sine, cosine, tangent, and you'll be asked to find the other information. So let's see here. We have a right triangle. Let's make one side, we'll say 2, and we'll make this side 3. That sounds good. So if you have 2 sides of the triangle drawn, how do you find the third side? So if I give you 2 sides of a triangle, and I just labeled it 1, 2, the other 3, nothing special. I don't know anything about the angles. How could I find the third side of the triangle? Think back to geometry.
The Pythagorean theorem.
Yeah, the Pythagorean theorem. If you know 2 sides of the triangle, we can always find the third when it's a right triangle. So a little reminder, Pythagorean theorem. A squared plus b squared equals c squared. So 2 squared, 3 squared, c squared. So Jenny, what does that give us?
That would give you 4 plus 9, which would give you 13, and then you have to square root it. And so the hypotenuse is the square root of 13.
Yeah. So do you think you want to keep that as a decimal? Or do you want to make that as a decimal?
Probably not.
Probably not, yeah. We're going to keep that as a radical. So we're going to keep it exact. So we're using the Pythagorean theorem to find the third side. Now that you have the third side, you're asked to find the 6 trig functions, knowing that the sine is the opposite over the hypotenuse. So I made the angle at the bottom. They'll give you where the angle is. I picked the bottom. So the opposite is 3, oops, and the hypotenuse is root 13. But you also know that you can't leave a square root in the denominator, so we have to rationalize. If you need to show the rationalize step, that's fine, but if you can skip it, that's awesome as well. So it would be 3 over root 13, but once you rationalize, multiplying both top and bottom by the radical, I end up with 3 root 13 over 13. So it doesn't seem like a nice happy number, but that would be the sine of an angle. Doing the same thing with cosine. Cosine is the adjacent over the hypotenuse. Again, if you rationalize that, you end up with 2 root 13 over 13. And then the tangent is opposite and adjacent. So that one's really easy to find. So Grant, how would we get the cosecant?
Would that be square root 13 over 3?
Yeah, what's the easiest way to find that?
Just do hypotenuse over the opposite.
Yeah, it's the hypotenuse over the opposite. Or you could take that sine and flip it around. So I had 3 over root 13, so just flip it. So hypotenuse over opposite, or the reciprocal of the sine. So same thing with cosine and secant, and then the same thing with the tangent and the cotangent. Pretty straightforward. So we've already done most of this. We're just adding those other 3 functions in. Example 2 says find the sine of 45 degrees, the cosine of 45 degrees, and the tangent of 45 degrees. So now they're giving us a value for the angle, where above we were just given lengths of sides. So we're going to label these angles. If one angle is 45 degrees, the other angle has to be 45 degrees. This was one of our special right triangles. So when you have a special right triangle, the 2 sides across from the 45 degrees, we said that both of those sides were B because they're both the same. They're both the bases or the legs. And we also said the hypotenuse was B and then the square root of 2. So this is just the special right triangle for a 45-degree angle. We don't know anything about the length of the sides of the triangle, but it's still asking us to find the sine of 45 degrees. Well, we know that the sine of any angle can be found by taking the opposite over the hypotenuse. That's what it says up above here. So the sine of theta, theta represents any angle, just like x represents any number. So I should be able to find the sine of 45 by taking the opposite over the hypotenuse. Well, my opposite side of 45 degrees is just b. I don't know what the actual number is, but I know that it is the value of b. And I know the hypotenuse is b square root of 2. Peter, what happens when you simplify this?
Would it become b squared root of 2 over 2b?
It would, but what could you do with the b's first?
Oh, I guess you could cancel them out.
Yeah, we could cancel them out so that they're not there. And then I end up with 1 over the square root of 2, which, Peter, that would become?
Square root of 2 over 2.
Yeah. So notice that the length of the side is actually irrelevant because it cancels out, because the opposite and the hypotenuse both contain the length of the side, and because you're dividing, it cancels it out. So Peter, do you remember on the unit circle, what is the ordered pair for a 45-degree angle?
It's square root of 2 over 2, square root of 2 over 2.
So a 45-degree angle on the unit circle is the square root of 2 over 2, square root of 2 over 2. Notice how it's exactly the same if I find it with a triangle as well. And that's the other perspective of trig. So you can use the unit circle, or you can really just construct a triangle. You get the same value. It's just depending on how you want to think about the answer. So if I want to find the cosine, I know it's adjacent. Well, the adjacent side is b. The hypotenuse is b root 2. And using the same thought process, I know that that makes root 2 over 2. And then the last one they asked us was the tangent. Well, the tangent would be B over B, opposite over adjacent, or just 1. But these values are the same values of a 45-degree angle on the unit circle. So you can find them by making a triangle. You can find them by thinking about the unit circle. Questions? So the next one says 30, this cosine of 30, or sorry, the cosine of 60, the sine of 30, the cosine of 30 and the sine of 60. So I know this triangle isn't drawn to scale, but pick one angle and call it 30, pick the other angle, make it 60. Technically one side should be bigger than the other, but they look about the same. So when we had a 30, 60, 90 triangle, that's a special triangle. We said the side across from the 30 was A. 60 was A root 3, and then the hypotenuse was 2A. So special right triangles have special patterns on a way to find their side. So cosine of 60, sine 30. And then cosine 30, sine 60. So you may already know what that is from the unit circle, but again, you can just make a little triangle as well. So if I'm looking at 60 degrees on my triangle, that's the upper top. If I go adjacent, it's A, hypotenuse is 2A, which makes 1/2. The sine of 30, now I'm at the bottom, going across for opposite, it's A, hypotenuse is 2A, the sine is 1/2. So the cosine of 60 degrees and the sine of 30 degrees are the same. And if you think about those ordered pairs on the unit circle, that happens the same way for the sine of 30 and the cosine of 60 on the unit circle. The cosine of a 30-degree angle would be A root 3 over 2A, but my A's cancel and I get root 3 over 2. And the same thing for the sine of 60 degrees. So again, the goal is for you to realize that the length of the side is irrelevant. It's the pattern of the actual triangle, the special right triangle, that gives us the value of the angle. Because a sine of 30 degrees, the angle size remains the same in a triangle that's big or a triangle that's small. So the sine of that angle is going to be the same value. Any questions? So the top of the next slide says because 30, 60, 30, 45, and 60, pi over 6, pi over 4, and pi over 3 occur so frequently, you could learn to construct those triangles that we have above. So any triangle that is a special right triangle corresponds with a 30, 60, 90, or 45, 45, 90. You can always make a quick little triangle and then find the values for sine, cosine, and tangent of those angles. You can also probably get them memorized just because we're using them so much. But see if you can fill in these 9 values. So the sine, cosine, and tangent for 30, 60, 30, 45, and 60-degree angles. And again, you can just look up above. You've got the triangles already drawn. So you could always draw yourself a quick triangle and label the sides of the triangle with those special right triangles. Tangent's a little trickier, so kind of look at your picture, look at that triangle. Tangent is opposite over adjacent. So my opposite for 30 degrees is A. The adjacent for 30 degrees is A root 3. Tangent of 45 degrees would be 1. And then the tangent of 60 degrees is A root 3 over A, which is just root 3. And I'm just using the diagrams that we drew above. So the last little thing on this page is to kind of get you to recognize a relationship between the cosine of 60 degrees and the sine of 30, and the sine of 60 degrees and the cosine of 30. So if I look at those, the sine of 60, cosine 30, cosine 60, sine 30. Jeremy, what do you notice about those values?
They're the same.
Yeah. So the cosine of 60 and the sine of 30 is 1/2. The sine of 60 and the cosine of 30 is root 3 over 2. But they're both the same. So underneath, it talks about co-functions of complementary angles. 30 degrees and 60 degrees add to be 90 degrees. Those are complementary angles. When you have angles that are complementary, functions kind of get partnered together and they're called co-functions. The bummer about trig is that there are so many little facts. When you learned math back in, I don't know, preschool, and you started talking about numbers, and then in kindergarten, you started talking about patterns of numbers and patterns of adding, like you have been learning facts about math since you were very young, and facts about numbers. But you've had since you were about 3 or 4 up until now to learn all of those different facts. Trig, unfortunately, has a whole bunch of facts for you to learn immediately. And one of the facts about trigs and angles is that co-functions of complementary angles are equal. Now, this isn't the same as reciprocal functions. So co-functions would be sine and cosine. They make sense because they have a co in the word. So the co-function, the sine and cosine, are co-functions. The tangent and cotangent are co-functions. And then the secant and cosecant are co-functions. Those values are equal if you're dealing with complementary angles. So if the two angles add to be 90 degrees, then the value of the functions are the same. So co-functions of complementary angles are equal to each other. So this says find using co-functions of complementary angles. If they give you the sine of 62 degrees, that is going to be the same as the cosine of what angle? Because the sine and cosine are equal. So if you have a 62-degree angle and you have the sine, if you have complementary angles, then co-functions are equal. So what would a complementary angle be to 62 degrees? Peter, what's a complementary angle of 62 degrees?
Would it be 28 degrees?
Say it with a little more confidence, Peter. Those two values are the same. So if you have a calculator, in your calculator, you can type in the sine of 62 and the cosine of 28. And I'll pull up mine. So sine 62, cosine 28, and you can see that their values are equal, and that's because they are co-functions. So as long as the angles are complementary, then the value is the same. So if we look at the next one, it gives us the tangent of pi over 12. Well, tangent and cotangent are co-functions, but we need to find the complementary angle. So remember, complementary, two angles that add to be 90, or two angles that add to be pi over 2. That's how you get the angle that it would be co-functions with. So I would subtract pi over 12. This has to become a 12, so I need to multiply the top by 6. So 5 pi over 12 is complementary with pi over 12. So the tangent of pi over 12 and the cotangent of pi over 5 pi over 12 are co-functions. It is not a fact that gets used often, but you will see it every once in a while. And you might see it written as the notation above where it says 90 degrees minus an angle. So just think the word co-sine and cosine, like it makes sense they should go together in some format. And they do. It's because they're co-functions. Does anyone have questions? So that's all the notes that I have today. I wanted, though, to start the homework with you because it's some application problems. So I wanted to kind of get you to see how a word problem actually correlates to creating a triangle in trigonometry. So if you still have that packet open and you slide down to page 29. Page 29 has 3 questions where you're going to draw a diagram from the problem, and then we're going to try and answer it using a trig function. And I thought I'd do number 3 because we very rarely see a sun in Pittsburgh, and this one talks about a shadow, and I'm not sure you're going to find a shadow today. I don't really remember the last day it was sunny. It's been a while. We've had a lot of rain and snow. But number 3 says we have a 40-foot flagpole. So I'm just going to start with that and draw myself a 40-foot flagpole. So there's my flagpole. There's my cute little flag. Put a couple stars on it. Make it look a little interesting. I'm going to label this 40-foot flagpole. That's how tall the flagpole is. It says it casts a 30-foot shadow. Grant, where is a shadow usually located?
On the ground.
Yeah, on the ground. So the sun must be sunny. I don't have a yellow. Let's see. There's a yellow. So here's my sun. In theory, it's sunny. And its rays are casting down on my flagpole and making a shadow, which would have to be on the ground. Maybe my shadow's a little too long, 30 feet. That looks better. That shadow is 30 feet. It says find the angle of elevation of the sun. So I'm going to make a triangle, since trig is the study of triangles, and connect my 2 remaining sides together. The angle of elevation is the angle that will be looking up to the sun. So if you were standing at the end of the shadow, you would be facing upward to the sun. Now, you're not supposed to look at the sun, but that's where the angle would be located. So I'm standing at the end of the shadow, looking toward the top of the flagpole. The angle of elevation is the one that looks to the top of the flagpole or up to the sun, because you're elevating your head to look up to the sun. So our goal is to find that angle theta. So I just wrote it as theta because I don't know what it is. If this is your angle in this bottom corner, and you're given two sides of the triangle, what two sides of the triangle would those be with respect to that angle? Peter?
Opposite over adjacent, or opposite and adjacent.
Yeah, opposite and adjacent. And you were perfect by telling me it's opposite over adjacent. So we have the opposite side and we have the adjacent side. Peter, if you have the opposite and adjacent, what trig function is that?
That would be the tangent.
That would be the tangent. So if I take the tangent of my angle and set that equal to the opposite and the adjacent side, we now have a proportion. The tangent of our angle is equal to, I'm going to cancel out the zeros because they both have a 0, 4 over 3. Now here's the weird part that we haven't done yet. Our goal is to find the angle. And there is a way on your calculator to find the angle, because we still want to know what angle that makes. What is the angle? I know the tangent of it is equal to 4/3, but we want to know what the actual angle is. So our answer should say theta equals something. We're actually going to solve for that. If you look on your calculator, does anybody know how you could find the angle? Anyone in physics right now?
Don't you hit the second tangent button and
Yeah.
then 4/3?
It is the second tangent. Above that, it says tangent -1. You're doing the opposite. We're taking the inverse to find the angle. And then as Jenny said, you type in 4/3, you hit enter, and that angle should be in degrees if your calculator is in degree mode. So my calculator is in degree mode. So my answer is a 53, we'll say 0.1 degree angle. Nice job, Jenny. So you have two other problems that are similar. Draw yourself a cute little picture. And then there are some problems in the book dealing with SOHCAHTOA and the Pythagorean theorem. Are there questions? So tomorrow will be a little more interesting. We're going to talk about some trig identities tomorrow. Little quiz on Thursday and Friday this week. Have a fantastic Tuesday.
I'm just
Have a
gonna
good day.
Thank you. Have a nice
Yeah.
day.